Good evening, myself Vaibhav Khan Singh. Today in this video we'll be having a discussion on Banker's algorithm. In the previous video we made a discussion on what deadlock is, what is the system model that which the operating system it prescribes, making a utilization of which the process it is making a request, it is able to obtain resource and then make is able to make a utilization of resource and then it is going to make a release of it. So a model is there. Beside that we made a discussion on what the necessary conditions of deadlock are, that is mutual exclusion, hold and wait, no preemption and circular wait. Beside that we had a discussion on resource allocation graph algorithm, resource allocation graph. Then we had a discussion on what all techniques we can make a utilization of so that we can handle deadlocks. Beside that, one approach, that is deadlock prevention, we had a discussion on that. Beside that, we had a discussion on deadlock avoidance and one method where a single instance of resource type it is there. The method, that is resource allocation graph algorithm for deadlock avoidance, also we had a discussion on that. Beside that, we were having an overview of what Banker's algorithm is and what all data structures it makes a utilization of so that it can achieve the objective it is supposed to achieve. Now, what deadlock avoidance is? Deadlock avoidance, the idea is to ensure that deadlock it never happens in the system. How it is achieved? The processes, they are giving some additional information regarding what all resources they will be requiring during their lifetime, the maximum requirement, and many information of this type is given to the operating system, and by having the information, the operating system it is in a position to decide when a request it appears from a process, it is in a position to decide whether the request is to be immediately granted or the process it is supposed to ask, the operating system will be asking the process to wait, depending upon what the scenario is. So operating system, how it will be saying that you are supposed to wait is on the basis of checking the resource allocation state, and on the resource allocation state what the operating system does is it tries to identify whether a safe sequence it exists or not. Now a question comes, what a safe sequence is? A safe sequence is an order of processes where the idea is allocation of resources. So we are having some processes which are in some sequence, and the operating system is actually allocating resources to these processes which are in a specific sequence, and if a sequence it is existing in which the operating system is able to grant resources to the processes in some way such that it is able to avoid deadlock, what maximum resources the operating system is having, and if it is able to make the resource allocation in some way or the other, that it is able to avoid deadlock. If a sequence is existing, then we say that it is a safe sequence, and if a safe sequence it is existing, then we say that deadlock, that the system it is in safe state, and if safe state is there, then we say that deadlock is not there. So here in Banker's algorithm we'll be actually trying to search out for this safe sequence. We'll be having a problem where we'll be trying to search out whether a safe sequence it is existing or not, and when we'll be seeing the problem, we'll be having a much better idea of what safe sequence is. Then Banker's algorithm, the name says that some inspiration or some analogy will be with what happens in the banks. So when you see the approach, the policy that which is utilized in banks, there is an analogy with that. You will find that similarity is there in the two approaches. So Banker's algorithm, there is one algorithm that is called safety algorithm, and before starting safety algorithm there are certain data structures which the Banker's algorithm it makes a utilization of. The first data structure is max. As I already told you that deadlock avoidance, some additional information is supposed to be given, and the additional information may be regarding what the maximum requirement of a process it could be. So max matrix, max it is a matrix which is of size n cross m, where n it is the number of processes, m it is the number of resource types. So n cross m matrix max, which specifies what is going to be the maximum requirement of a process in terms of resources. Then we are having another matrix, that is allocation matrix. Again the size it is n cross m, where n it is the total number of processes, m it is the total number of resource type. Allocation says that what information you will find in allocation is a particular resource allocation state is there. At a particular resource allocation, what is the amount of resources of each type allocated to a process, we'll be able to find out by means of this allocation matrix. Then we are having another matrix, that is need matrix. Again the size it is n cross m, where n it is the total number of processes and m it is the total number of resources or resource types. So then need matrix, it will be there will be a difference between what the maximum requirement is and what is allocated. So the thing is, if a resource type A is there and the maximum requirement, suppose a process is there, the name of the process is P0, the maximum requirement of process, the maximum requirement of a resource type A by process P0, if suppose it is 6, and out of 6 it is allocated 4. So in max, on behalf of A, value 6 will be there, and in allocation on behalf of A, the value 4 will be there. So in need there will be 6 minus 4, that is 2. So the two matrices, that is max matrix on behalf of A, will be having value 6 if the maximum requirement of process of resource type A, process P0, the maximum requirement that it is having of resource type A is 6, and what allocation the operating system it has made at the point of assessment, it is 4. So what more required is 2. So need matrix will specify that value. Max minus allocation will give need. Need matrix will specify what more is required to accomplish the task, and then we are having a vector that is available. Uh, a system, it is going to have many resource types it can have, like we'll be seeing an example where we'll be seeing that three resource type specification will be there. So I'll be saying that if a system is there and a resource type A is there, so maximum number of instances of that resource type the system may be holding, like the system may be holding two CPUs. So maximum number of instances of CPU is 2. So if a process is there and the maximum requirement of resource type CPU it is 1, and what is allocated is also 1, so what will be in available? 1. One process is there, one is allocated, maximum requirement is of 1, say the maximum requirement is of 1 and 1 is allocated, and no other processes are there. So maximum is 2, 2 minus 1, the value will be 1. So in available, we'll be seeing what every resource type maximum value will be there, what is obtained by the system, what is the maximum value that the system it is owing of each and every resource type. Suppose of resource type A it is having 10 instances, of resource type B it is having 5 instances, resource type C it is having suppose 9 instances of these number. At a particular point the value is going to go down because some of the resources they may be allocated to some of the processes. So available will specify the value that is available at the point of assessment. So then we are having safety algorithm. Safety algorithm will make a utilization of these structures, these data structures which I just specified. Safety algorithm, the idea would be to verify whether the resource allocation state that which we are making an investigation of, that whether safe sequence it exists or not. So safety algorithm will be implementing the concept where we'll be trying to generate a safe sequence out of what resource allocation that which we are having. So safety algorithm, it comprises of 4 steps. In the first step we are having 2 vectors, work is there, finish is there. Work is initialized to a value what is there in available, it goes to work, and finish of I is initialized to a value false. Work, the size of work is m, where m is the total number of resource types, n it is the total number of processes, the size of vector finish is n, the size of vector work is m, work is initialized to available, finish of I is initialized to value false. So I can have different values starting from 1 to n. So it means that if 5 processes are there, you can have 5 elements in finish. If 5 processes are there, 5 elements are going to be there in finish, and every value, every element in step 1 will be initialized to value false. We'll be seeing one example and the concept will be more clearer. Then we are having step number 2. In step number 2, we are having we are performing a search operation where we are trying to find out a value of I such that finish of I it is equal to false, and 2 conditions are there, and we are trying to search out for a value of I where these two conditions they are true. The first condition is finish of I is equal to false, and the second condition is need of I is less than equal to work. If these two conditions they are simultaneously true, then we will be going to step number 3. Otherwise, we will be moving to step number 4. So, in case these two conditions they are true, then in step number 3, we are making an updation in the value of work. Work will become work plus allocation of I, and one more operation is there, finish of I, it is assigned a value true. So two operations they come into picture if we are able to find out a value of I such that the two conditions, that is finish of I is equal to false, is true, as well as need of I less than equal to